Okay. I will skip the Java update. Okay, so welcome to the mathematics of Legos. So the purpose of today's class is to just be a really fast, informal discussion of some of the places where mathematics actually enters into Legos and how we can use Legos to actually gain some insights about some really good mathematics problems. So I'm just culling these slides from other introductions I've given in previous years where we have not been so laser focused from the very first moment to getting the speed build done, essentially 1 week after we started with all the stuff going on with the pandemic. So, the first is just my Lego chops. This is, for my wedding cake, there was only 3 things I asked for at my wedding. One of them was to create the decoration on the top. And so if you have, reasonable asks, you actually have a chance of getting them done. And so if you ask for too much, you're not going to get it. But small, reasonable thing like a wedding top, that you can do. In the old days, when you could actually go to the library, they actually had Legos that you could just play with. And so this was one of my, fun challenges. Can you identify what ship that is? Yeah, this is where you need to know a little bit of science fiction. This is the Enterprise from Star Trek. And I think it's not, too bad to do it in just, 10 pieces. But this really indicates the difficulties of doing things with Lego. My son right now loves airplanes and is trying to build a really good, realistic jet airplane where he has all the different wings and flaps and the wheels retract and whatnot. And to do things with the scale of Legos, if you make it a reasonably small scale, you just don't have enough to have the detailed work you want. And if it's huge, then the number of pieces you need is absolutely astronomical. So it's an interesting question. How much do you need before you can get a pretty good sense of what's going on, as well as which kinds of pieces do you need? So one of the key pieces in this is actually a right angle piece. I should have brought them down. I had them in my office. It's take a 2x2 square and remove one of the corners. So you have 3 dots in basically a right angle. We didn't have pieces like that when I was a kid. And so, again, the complexity of sets has greatly changed since I was a kid. It's both good and bad. The sets when I was a kid sucked. You would never want to keep it built because you could do better. And in fact, it encouraged you to do better. Nowadays, the sets are phenomenal. They've got roller coasters that work. They have Star Wars ships that look better than the plastic models you buy. And so there's less of a desire to just take them apart and just play with the pieces. And it's much more structured play, which I don't like. So if you needed something when I was a kid, you actually had to create something. Nowadays, they have their own pieces. Now, there is a disincentive for Lego to have many pieces because the more pieces you have, the more molds you have, and the more expensive it's going to be to build a set. So frequently, they will encourage their designers to use as few pieces as possible, few different types of pieces as possible in the constructions. All right. So I'm just going to go to, okay, so unit analysis. So, again, the goal today is to talk a little bit about how do we describe and discuss problems in the real world. So do you have any idea what's so special about this bridge in the Boston area? So fraternities are no longer allowed on campus. I will not go into why, because this is being recorded. But it turns out that in many places around the country, you can do almost anything with your pledges. And so decades ago, one of the fraternities at MIT was curious as to how many times would we have to pick up and drop one of our pledges before we made it from one end of the bridge to the other. And so, Smoot was the lucky pledge who was chosen. And the answer was 364 smoots plus or minus 1. I'm sorry, 0.1 smoots plus or minus an ear. And every time they picked him up and put him down, they put another mark. Well, the Cambridge police were not thrilled with this, and they removed the smoot marks. The fraternity was not pleased with this because they did a lot of work to get these smoot marks done. And so they then redid this. And it went on for a while, and eventually the police said, screw it. And the smoot marks stayed. They've now been institutionalized. There's now smoot markers on the bridge. And if you read the traffic reports, they tell you how many smoots from the edge of the bridge the traffic accident happened. Is the smoot a good unit of measurement? No. One thing is it's very hard for someone else to figure out, well, what is a smoot? If I want to measure things in smoots, I need access to smoot. It's an interesting question to think, how do we define the fundamental constants in the world? So initially the meter was defined as the length of a specific object that was in, I think, Paris. Now the meter is defined in terms of how far light travels in a certain number of vibrations of an atom. And so the speed of light is a universal constant. It's now time that we define. And from the speed of light and time, we then get the meter. So you really want to try to find statistics that describe the world well. I do a lot of work in baseball statistics, a lot of work with Williams students. I don't know how much of a baseball fan you are. So there's a lot of statistics in baseball that are just absolutely horrible, but they sound good. Probably the best example of a statistic that's bad but sounds good is the save. When you hear he saved the game, you feel, oh my God, it was on the line. If it wasn't for this wonderful performance, all would have been lost. Well, the way a save is defined is if you are the last pitcher and your team is leading by 3 or fewer runs, and you don't relinquish the lead, you get the save. But there's another way you can get the save. It doesn't matter how much of a lead you have, as long as you pitch the final 3 innings. And so years ago, the Baltimore Orioles were playing the Texas Rangers, and after 6 innings, the Rangers were leading 14-3. So you have an 11-run lead, 3 innings left, there's 3 outs an inning, so there's 9 outs left. You could alternate home run out, and you would still win. Texas brought in a relief pitcher who pitched the final 3 innings. Texas scored 16 runs in the middle of his pitching performance. He let up none. So with 16 runs of support, coming in with an 11-run lead, he ends up with the save. Now, Billy Beane, if you've ever done anything with Moneyball or heard anything about this, he was the general manager of the Oakland A's, and he was part of the movement to look at which statistics really describe what we care about, which help us figure out how do we win. And they found that people were overvaluing some things and undervaluing others. People overvalued batting average, hitting the ball fairly and getting on base, versus on base percentage, which also takes into account walks. The batting average doesn't take into account walks. And there's a whole alphabet zoo of statistics you can look at now. But the point of this is we want to find good statistics to describe the world. Smoot is a bad statistic. MIT is famous for a bunch of statistics. The Bruno is another great one. It's the indentation in cubic centimeters from dropping a grand piano from the 3rd floor of one of their buildings. Millie Helen is another fun statistic to look up. Now, what I love is, when you tell stories like this, sometimes they just have endings that oh, wait a minute. Oh, I didn't put in here. Okay, here we go. You never know where things will lead. One of the things in life is I always want you to be ready for whatever opportunities arise. Oliver Smoot, the person who was used as the unit of measurement, ended up becoming the chairman of the American National Standards Institute and the president of the International Organization for Standardization. Now, you could easily see him getting upset as he's being used as basically a giant meter stick. Or he could just say, you know what, I'm going to roll with it. I'm going to just have fun with it. It's going to happen. It's going to give me a great story to tell people for the rest of my life. There's a great saying, you're 1 in a million, which means there's 1,000 like you in China. You need to figure out how you're going to distinguish yourself from other people. My first winter study class I ever taught was on the mathematics of encryption, and I encrypted the title of the course, and it showed up on the Williams transcript encrypted. And it was a conversational starter for a lot of people when they were applying for jobs. People said, what is this on your transcript? And so you never know who's going to be able to help you later. So always be on mind, don't burn bridges. Now, the reason I was talking about trying to find the right unit is here is a Star Wars set. It's an X-Wing. How should we figure out what the cost of this is? Imagine we're Lego and we're trying to figure out how we should cost it. What are some things that you think might be appropriate? And for those of you in Zoom land, feel free to speak up as well.
Number of pieces seems like a good starting place.
Yeah, number of pieces is a great starting point. So the simplest thing, and again, you often do the first order approximation. Let's just do it straight by the number of pieces. The more pieces you have, the more expensive. What's wrong with that? Yes, some pieces are more complicated. Some pieces are maybe larger and they cost more to make, or they have a more intricate design. But maybe that will roughly cancel out. And maybe a lot of these effects, maybe if I just do a quick cost by number of pieces, that might not be so bad. And so this, when I gave this talk, the first time, there were 560 pieces in the set, cost $120 or 21 cents per piece. So I'm introducing, cents per piece as a reasonable unit of measurement to try to describe a Lego set. I don't think this is the perfect unit, but it's not bad. If you're a football fan, you can think about the quarterback rating, which is a very good statistic, but it's a very hard one for a lot of people to really grasp because it has so many different things that feed into it. But at the end of the day, it gives you just a nice number where 100 is a really good score. So a simple statistic like cost per piece or cents per piece is not going to capture everything. And so this would probably be the start of a more complicated statistic. So here is another set. It is a frozen set. It's interesting as to how old you guys were when Frozen came out. So this is 292 pieces for $65 or 22 cents per piece. So pretty similar. Now, what do both this Frozen set and this Star Wars set have in common with each other that they may not have in common with other Lego sets? Say a Lego fire station or a Lego townhouse.
These are connected with like really important childhood memories.
Okay, one is they're connected with childhood memories, but it's more than just childhood memories. Movies, they're connected with really big multi-billion-dollar companies. In fact, both of them are connected with Disney now, because Disney has now bought Lucasfilm. So when you're trying to figure out the cost, Disney is not going to let you build stuff for free. They're going to hit you with a charge. And depending on how much they ask, you might say, screw it, it's not worth it for me. Let's see, you were all too young to remember when Star Wars: The Phantom Menace came out. It was the first Star Wars movie in a long time. We had high hopes for it. I was a graduate student at the time, and I arranged for 300 tickets for opening night. And we had a bunch of us waiting in line to get the tickets. And so a lot of hype, a lot of people really wanted to see it. Several movie theaters chose not to show The Phantom Menace because George Lucas said, look, if you're going to show The Phantom Menace, you have to have a sound system at least this level. I guess if you don't hear Jar Jar on your 3D, whatever, it doesn't sound right. And you must commit to using your largest rooms. And you must commit to doing this for so many weeks. That the deals he imposed, most people said, yes, whatever, please, yes, we want to show you a movie. And some people said, so many theaters are going to be showing Star Wars: The Phantom Menace. Yes, we're going to get a lot of people who will want to see it, but we're going to give up so much to get it that it's not worth it. And for this, you want to know a little bit more about how movie contracts are structured. So I teach a class in operations research, and I'll probably be teaching that next year. It's a nice mix of math, statistics, computer science, marketing, psychology, economics. And so I've actually worked with multinational movie chains where they have to decide what movies they want to buy and sell. How do you think movie theaters make money? So one is the tickets. What else? Yeah, the reasonably priced concessions, right? Right. And so there are some movie theaters that basically just show old movies for like $1 because they don't really care what they show. They just want to get people in the door to watch movies and buy stuff. Especially if it's a hot day, if you're in a climate where it's very warm. And so the way the contracts work with the movie companies get the highest cut of the ticket revenue in the first week. And then the longer the movie's been out, the less the movie company gets and the more the theater gets to keep. But of course, most movies have a decreasing demand as time goes up. You have a few movies, Blair Witch is probably one of the most famous, that start off with a very small number of people seeing it, and then it spreads word of mouth, and it becomes one of these, surprise hits. But most of the time, the demand decreases. And so when you're trying to figure out what's the right set of movies to buy for a theater, it may not be advantageous to buy the movie that everybody's going to want to see, because so many other people are doing that, and the cost for doing that is so high, you might actually make more money doing something else. So when we're trying to figure out, what is the cost of a Lego set, the two examples I gave you, the X-Wing and the Frozen Castle, which would be fun to play with them together, they're both coming from the Disney line. And you might wonder, well, how much of that, 21, 22 cents per piece is actually coming in royalties that you're paying to Disney? When I was a kid, there were no Lego lines. Now you have the Harry Potter lines. You have special sets like from Lego Ideas, the Friends and the Seinfeld, Big Bang. And you wonder, how are the revenues, split in something like that? The first year we did this, we did the Superstar Destroyer. And, depending on how you're able to find it, was around 19 to 25 cents per piece. The London Bridge was 5.6 cents per piece. So the Superstar Destroyer, 3,152 pieces, on the order of $600 to $800. The London Bridge, 4,000 plus pieces at a cost of 5.6 cents per piece. So part of this could be the fact that, the London Bridge, you don't have to pay royalties to Her Majesty. Why do you think the Superstar Destroyer might be so much more expensive than the London Bridge? Which, if you want, both of them are in my office. Any thoughts?
Royalties, or just the...
Well, so part of it is almost surely going to be the royalties given to Star Wars, but that shouldn't be enough to explain the fact of almost 4.
demand?
So part of it is also demand. And there was one day where we had a 4th of July parade where we actually had 4 built Superstar Destroyers going down Spring Street with the Imperial March blaring. But there's another reason, and I don't know if you can see things well enough, if you can look at this set and really tell. But if this one has, 4,000 pieces, how complex are these pieces? If you look at it, you keep seeing, you're going to have a lot of the same brown pieces again and again and again. So the piece complexity is very low. So in terms of just assembling the set to sell, this is actually a much cheaper thing to do. And so, the cost per piece, just looking at the number of pieces, that might work for most things, but there will be some exceptional situations. And this is a good lesson to learn in life that, stock market is a great example. You can have methods of investing that work most of the time, and then when the market is crashing, your methods are not working. And unfortunately, those are the days when fortunes are won and lost. And so when you're designing things, you need to be very careful about these key moments. And so when we're trying to figure out the complexity of a set and how that should affect the price, maybe just a simple estimate of, first order, most sets are going to be similar in terms of complexity, maybe in terms of royalty. So we say, as long as there's some royalty, around 21 cents per piece. But that won't do everything, and there will be some exceptions, and those exceptions will tell you interesting things. Okay, so I'm going to skip the investments, Lego ideas. Okay, so here we were coming up with trying to build, what was it from? Is that what it was? This was from one of the, I'm blanking now on the TV show, I never watched it. There's like a castle, one of those Empire movie TV shows. Oh well. So the students were trying to determine how much they should sell their set for. And they would have some idea of how big it was going to be. They were going to try to create a castle from a TV show. And here's a plot of your sets. On the x-axis is the number of pieces, and the y-axis is the price. And you can see that there does look to be a pretty linear relationship in terms of for most sets. Now, as you start going to the extremes, you start to see deviation from the line. And again, this could just be the fact that, something that works well in small values is going to start to break down, that there could be some efficiencies of scale. You could be in some new phenomena. If you know any physics, there's the special relativity versus just Newtonian mechanics, that speed is not additive, but you're not going to see that at small things. Well, if we put in the names of the different things, you see that one of the biggest outliers is the Tower Bridge in terms of the price. And the rest of the stuff, if you draw the straight line, the Disney castle is still actually pretty much aligned. That the Death Star is a little bit higher than you might expect. But again, that could be just the thought of having your own Death Star. It's also a really fun set. I've never bought that one, but it looks very playable. But the Tower Bridge is very off the line, and it's a much simpler set to look at. And so I'm going to skip that and just talk a little bit about Legos and science. And so here is a beautiful plot. And this is just an opportunity. We talked a little bit about this early in the semester to discuss logarithms. So most of the time when people see logarithms in high school, you're just taught that this is just yet another function you should look at. And okay, we can take logarithms, we can take derivatives of logarithms, we have all these things, but you're not really taught why we care about logarithms. The reason we care is they allow us to discuss phenomena that span a tremendous number of orders of magnitude, all in one slide and all together. To be able to talk about an atom and a galaxy on the same slide, when you just look at the incredible gulf between them, is amazing. And so here, we're going from something of size 10 to the -4 to size 10 to the 8. That's 12 orders of magnitude. And so this is a plot, it doesn't really even matter what it is, but it's like optimal cruise speed at sea levels versus mass. It just talks about how different flying creatures have had to evolve and solve problems like this. And an incredible law that's going on. Now, if you look, there's a data point that is very far off the line. Is that surprising? No, why not? We don't fly. So, be very careful what you use things for. If we have a extrapolation coming from mass and flight, don't put in a human which doesn't fly. Now, what is interesting is if you look, you see the F-16, the F-40, the 777, the 747 actually pretty much follow that line. And again, there's incredible value of looking at things at small scales and extrapolating upwards. What you can also do is you can plot Lego sets by piece complexity. So doing log-log plots is one of the most important things to do when you're gathering data. It's a wonderful transformation. It allows you to look at complicated phenomena and frequently convert it to a linear relationship. So if you have something is proportional to the square or the cube or the reciprocal, these are going to be tough relationships to look at and tell, well, what's the difference between something to the first power, to the 1.2 power, or the t log t. But if I do a log-log transform, if I just have it to some power, that power then comes in as the slope. And so here we're plotting a bunch of different Lego sets, and the y-axis is the log of the number of pieces, of the number of piece types, and the x-axis is the log of the number of Lego pieces. And you see that, for a lot of sets, not surprisingly, there's this general growth, that as the set gets larger, there's more and more pieces, there's more and more different types of pieces. We're not just making something with the same building set. As our set gets larger, we're trying to build something larger, and we need more complex pieces in order to be able to do this. You could, of course, compare this to the evolution of objects, of biological organisms, in terms of how many different types of cells and whatnots do you have. And so here, again, this is just zooming in on this, just looking at an incredible, almost linear relationship between the number of piece types and the number of pieces, again, on a log-log scale, and seeing that linear relationship. And then you can look at this in terms of some natural phenomena. So the one in B is the number of substrate types involved in metabolic pathways versus the number of metabolic pathways in which they are involved for 43 different organisms. Again, You can find so many examples like this in science. It doesn't really matter which ones you do, but you see these wonderful relationships. And this is not meant to be an intense math course. This is meant to study. It's not supposed to be that. The goal is to just put a few key ideas on your radar screen so that later in life, you are aware of these things and these just become part of your tool set of just things to ask. So when I do pure mathematics, whenever I see a product, I always think about taking logarithms because I can work with sums with much greater ease than I can work with products. So let me take a logarithm and see if that helps. When I'm trying to understand data, a lot of times doing a log or log-log transformation makes the data much easier to study. All right, the last thing I want to just talk about, and then we'll end up with a little bit of Lego art, is just counting problems with Lego. And so one of the most important things, and we've talked about this a little bit earlier in the course, is how do we want to count things? So we talked about tic-tac-toe, that you can view tic-tac-toe as there are 9 opening moves, or if you consider symmetry, there are really only 3 opening moves: center, middle, corner. And you can look at the different responses and whatnot. One of the things you have to be careful about is, do you consider mirror image the same? So if I'm just trying to analyze a tic-tac-toe game and see who's going to win, I don't care if one game is the mirror image of another. The game is essentially the same. And so in terms of trying to determine what is a good strategy for tic-tac-toe, I make no distinction between a game and its mirror image. Since you had mentioned computer science, have you ever written a tic-tac-toe program? This is one of the easiest choices if you want to make a game where you have a computer play a human. So the 0th order opponent just plays randomly. The 1st order opponent looks to see, do you have a chance of getting 3 in a row? If yes, I block. Do I have a chance to move somewhere to get 3 in a row? If yes, block. So you can then program a harder opponent without too much trouble. And then if you want to go a little bit further, you can even program a very intelligent computer. There's not that many cases to analyze in tic-tac-toe. And so it's a great example of just being able to have different levels and whatnot. So when we're doing the analysis there, a mirror image game makes no impact at all in what's going on. When you look at the human or the real world, however, if you look at various compounds, the mirror image of a compound is not going to interact with you the same way. And the mirror image of something that actually helps you could actually hurt you. And so there, when we're doing counting, we want to consider that we may distinguish between a orientation and its mirror image, which makes things much, much harder. I'll skip the God number. So the number of ways you can combine 6 2x4 Lego bricks of the same color, so ordering doesn't matter, is 915,103,765. Now you have to be careful by what you mean by combining. So here you have to snap a brick on cleanly. You are not allowed to have it pivoting at an angle, because as soon as you have it pivoting at an angle, you actually have infinitely many ways to do it. So every connection must be at a right angle or parallel, one or the other. Now, one of the hardest things to do in life is to recognize when you are making an implicit assumption. So when you look at this picture, what do you think must be true about the structure that you're building? Okay, so it follows those sorts of rules, but there's another rule that I haven't explicitly mentioned that a lot of people assume must be true when I give them this problem. So one is that you have to use them all. So let's say you have to use them all, but that's a good question. What if we don't have to use them all? So then you would say maybe the number of ways you can combine at most 6 bricks. So let's say we have to use them all. What else does this picture seem to suggest is happening? Again, it's so hard to tell when you are implicitly assuming something. Where do you think this Lego minifigure is going to put that last brick? Does that minifigure have any choice as to where the last brick is placed? Yeah, so it seems to be implying that you're going to combine them and have something that's 6 units high. So one possibility is, could I have 4 bricks connected to each other and then 2 others connected to each other? Is that allowed? Or maybe I don't have to go as high as 6 units up, but everything has to be connected. And so when this was originally stated, it was implicitly assumed that you had to go all the way up. But you could actually go up 4 and come down a bit. And so it makes the problem a lot more interesting. So if you're interested in computer science and combinatorics, this was a really interesting problem figuring out how to do this. The one I skipped, was the Rubik's Cube. It's called the God number. If you gave God a Rubik's Cube, no matter how it's mixed, how many moves would it take God to solve? And part of it depends on what you define as a move. So is a move a quarter turn, or could a move be a full half turn? And of course, if you do a quarter turn one way, that's the same as a 3/4 turn in the other direction. And it turns out they finally were able to prove that for a 3x3 cube, you just need 20 moves. And there is a configuration that requires 20 moves. So 20 moves is the God's number. For the 2x2, it's 11 if you can use half moves, 14 if you have to use only quarter turns. We don't know what the God's number is for the 4x4 and high because there's just so many cases. And so these are tremendously difficult computational problems. In terms of machine learning, they've now created algorithms that are given Rubik's cubes and are just given the rules of how you mix them up. And these artificial intelligence, well, I won't say artificial intelligence, I'm not qualified to say whether or not it's that. These machine learning algorithms can figure out how to solve Rubik's cubes by just taking solved cubes, doing a whole number of moves, and just watching what's happening and just building up a set of moves that allow you to fix various configurations. Amazing what you're able to do now. These are tremendous programming challenges. And these may look like kid toys, but you're trying to figure out, how does a computer learn how to solve the Rubik's Cube? Well, then you can use that for figuring out many things that are of real importance. So if we were looking at just 2 2x4 bricks, here's all the different ways to legally combine them in terms of having them at right angles or parallel. And then just starts getting worse and worse and worse as you go higher and higher and higher. And so there's a beautiful paper on the asymptotic enumeration of Lego structures, which actually goes through and discusses exactly how you would prove all of this. And so the number of ways to combine 6 pieces, if the height has to be exactly 2, 3, 4, 5, or 6, is the following. So interestingly, the largest one is actually of height 4. And when you have things of height 4, you have many different places where you can be coming down a little bit. Which kind of makes sense, because if you have height 6, you have a lot less freedom because you have to keep going up. And so interestingly, you start low, you go up until you get to 4, and then you start coming down as you go down to 6. Is this a general phenomenon? If we had to go up to 12, would we expect things to be clustered maybe in the middle as going to be the one that has the most complexity, not the extremes? The last thing to just enter before we go on to pictures, if you've never heard of it, the OEIS, the Online Encyclopedia of Integer Sequences. If there's a sequence of numbers that you want to know a little bit more about, you just go to this website, you input what it is, and it will tell you everything it knows about them. So here, I inputted the sequence, the number of ways, counted up to symmetry to build a configuration with n Lego blocks of size 2x4. So it is amazing what you will find on this website. Sometimes they will give you explicit formulas for things. This is so complicated, we don't have explicit formulas. You put in something like the Fibonacci numbers, and it will just give you pages of information of references and formulas. In previous years, we tried to build a suspension bridge. This was not ours. The first time we did this, we did a small proof of concept at the Mantle and Peresky. The next, I guess this is to zoom in. The next year, we did a long one on the ground floor. After we showed the college that it was safe to do that, the next year, they actually allowed us to build one, spanning the chasm. We worked with the Williams Outdoor Club to actually have students in safety harnesses as they were leaning over and connecting various parts of the bridge. there's a lot of just really beautiful art, and I'll just end with just a few pictures of Lego art. So I think this is from Scott Kenny, no, Sean Kenny. And just, again, I'm a huge superhero fan. The way it gives you the motion of Flash moving, which is of course phenomenal because this is a static piece of art, and just trying to find new interesting ways of using pieces. Sliding into base, ducks, playing cards. There's a lot of art now where, very similar to Impressionist, you have Lego sets now where you can just buy the giant base plate and a bunch of dots. And then just trying to figure out, how do we put the images there and get something that's going to be visible. All right, so this is basically all I wanted to say, is just to give you a little bit of a sense of the mathematical connections you can do with stuff like this.